Hello everyone. So today let's solve this one. Let's discuss the rotating calipers algorithm. Previously we had discussed on the topic closest pair of points algorithm, right? So today let's start with the rotating calipers algorithm. Let's get into the definition part. Let's see what it states here. The rotating calipers algorithm is a geometric technique. Yeah. So this is related to the geometry based algorithms itself. So it's a geometric technique that uses a pair or more of calipers, nothing but imaginary parallel lines that rotate around a convex polygon that rotate around a convex polygon to find extreme pairs or optimal geometric measurements. Yeah, to find extreme points or optimal geometric measurement, such as whether it may be width, diameter, or area efficiently, right? It transforms complex geometry problems into smaller linear sweeps. Again, it transforms complex geometry problems into the smaller linear sweeps, right? So let's get into the this one explanation part. Actually, listen to this carefully. So whatever we discuss here, the exact same thing we will be articulating in the form of code, actually, right? So let's imagine if we have a convex polygon. So suppose if we have the convex polygon, say a convex hull of set of points. So we have already discussed the convex hull algorithm, so we should be knowing the convex hull of the set of points, right? So now let's imagine placing two parallel lines. Suppose we have placed two parallel lines, right? So this one calipers nothing but that touch the polygon, one at an extreme point and another opposite to it, because we are considering two parallel lines, right? So one at the extreme point and other opposite to it. So this is fine. We rotate these calipers around the polygon. So what do? We rotate these calipers around the polygon, maintaining their parallelism. Maintaining their parallelism. At each rotation step, we measure something. Suppose for the example, the distance between the opposite points. The distance between the opposite points, as we have placed this one two parallel lines, right? We'll be calculating the distance between the two opposite points just to find the polygon's diameter, actually, right? So just listen to this carefully. Each vertex is considered only per rotation, right? So each vertex or the node is considered only once per rotation, sorry, making the time complexity big often, making the time complexity big often. So here whatever we discuss, the same thing will be articulating in the form of code, no worries. So some of the common use cases or the this one common applications are finding the farthest pair of points, convex polygon diameter, basically. Finding minimum bounding rectangle. This is also one of the use cases where we make use of the rotating calipers algorithm. The final one is finding width or height of the polygon. Yeah, so we are done with the algorithm part. We are done with the explanation part. Now let's try to implement the same thing in the form of code. Let's start writing the algo, right? First we need different math operations. So I'll just this one import math, right? So this is fine. Next, the first step, let's go with a helper method or the function just to calculate the distance between 2 points. Yeah. So I'll just go with def here, distance. Yeah. So within the distance function, sorry, what happened here? Oh yeah, sorry. Mention this one, right? P1 and P2 are the parameters that I need. So within the function distance, so let's go with a Euclidean distance between x1, y1 and x2, y2, right? So I'll just go with here return. I'll just go with math dot hypoth. Yep. So this is fine. I'll just go with P1 of 0. This is fine. Minus P2 of 0 as well. Yep. So again, so let me go with a P1 of 1 hyphen, sorry, not minus, this one minus itself. So this one will be P2 of 1, P2 of 1. Yep, so this is fine. Next, what we'll do, let's go with the rotating calipers function to find the polygon diameter. So basically we have to find the polygon diameter itself. Yeah, so I'll just go with the another function naming main function, actually, rotating calipers, right? I'll just go with calipers. Yeah, so this is fine, man. So let's do one thing now. Let me pass the points here. Let me pass the point. So within this function, first, um, I'll just go with the length of points. So we'll be making use of the length of the points everywhere. So let me assign this one to the variable. Yeah, so this is fine. Next, suppose if n is equivalent to the 2, then what we'll be doing? So let's return here. Let's return distance of this one, points of 0, points of 0, and points of 1, points of 0 as well as the points of 1. Next, what we'll be doing, let's initialize the max distance to 0, right? I'll just go with the max distance. Let me initialize this one to the 0. Also, let's go with the second pointer and let me initialize j to 1. Yep. Now let's move on with the third, this one, third step. So let's iterate through the each vertex. Let's iterate through each vertex, right? So I'll just go with for I in range n, for I in range n. This is fine. Let's go with the step 4. We have to move the j while the area increases, right? So nothing but next vertex further, right? So I'll just go with while of true here initially. While of true. So within the while loop, first thing, let me assign next here. This one to the j plus 1 modulo n, modulo n. Yep. So this is fine, I believe. Next, we have to go with a cross product to check the rotation direction, right? So let me copy paste this one. Just give me a second here. So I'll just paste it over here. So this is nothing but we are just going with a cross product to just check the rotation direction. Yeah. So this is fine. The next step would be after that, let me write the simple if condition here. If this one cross is greater than next cross here, if cross is greater than next cross, then let's do one thing. Let me assign j to next. Let me assign j to next. Next, I have considered nxt, right? So why it is not showing nxt? It is. This is fine. Else, let's do one thing. Else, let's consider we have to break from here, right? So I'll just make use of the break keyword actually, right? So this is fine. Next, let's do one thing. Let's go with the fifth step, nothing but we have to update the maximum distance between I and j, right? So I'll just go with the maximum distance equals max of this one. Let me pass the maximum distance here. Maximum distance. Uh, Let me go with distance of this one. Points of this one I and points of j, right? Points of I and points of j, right? So finally what we will do, let's return the maximum distance, right? So let's return the maximum distance. So I'll just leave here return maximum distance. Yeah, so this is fine. The next step would be let's go with the example, this one, convex hull, right? So this is it for the algorithm. Actually, it's very simple. Yep. This is fine. Next, as we have discussed the algorithm step by step, let's do one thing. Let's go with the example usage. Just the example usage, I'll just take this one from the Google. Just give me a second here. So I have pasted this one here. This is nothing but the example convex hull, nothing but square, right? So this one result, we are just finding the polygon diameter by calling the rotating calipers function, and we are passing the points that we have considered here, right? So this is fine. Next, finally, we are going with a print statement for the interactive purpose, nothing but we are just printing the result here, round of result comma 2. Yep. So the what's the output that we need to get? We have the idea on the algorithm completely. Now, what's the output that we need to get? So we are going with a maximum distance. We are passing the round result comma 2. Basically, let's discuss the output part here, right? So basically, what happens here? The given square points, whatever that we have considered here, 0, 0, 0, 3, this one, these are the square points, right? The given square points form a convex polygon. We know this, yeah. The farthest points are diagonally opposite, right? Either it can be 0, 0. The farthest points are diagonally opposite, right? It can be 0, 0, and the final, the last one is 3, 3. Sorry, 3, 3, or it can be this one 0, 3 and 3, 0. 0, 3 and 3, 0 and 3, 0, right? So the farthest points either can be this one 0, 0 and 3, 3, or 0, 3 and 3, 0, right? So the Euclidean distance we will calculate. So we can just calculate this one for these 2 points Euclidean distance, right? So we will be going with actually 3 minus 0 whole square here. 3 minus 0 whole square here, plus 3 minus 0 whole square here. So for this one, for this one also same actually. Same for both actually. So this one will be 3 minus 0 whole square plus 3 minus 0 whole square, right? So we have to this one take the result in the positive itself. So this one also doesn't matter. 3 minus 0, this one 0 minus 3. So the output will be in the form of positive number itself, right? So this is fine. So this one will be 3 minus 0 whole square will be 3 square. This one as well, 3 minus 0. So again 3. 3 plus 3, 3 square plus 3 square, we will get actually 9 plus 9, which is equivalent to square root of 18 actually. What's the square root of 18? Square root of 18, we have to get actually 4.24. 4.24 actually. So this is the output that we need to get here, right? So the diameter of the convex polygon is 4.24 units, 4.24 units, right? Accordingly with the algorithm that we have written. Simple, very simple one, right? So now we have the idea. Let's do one thing. I'll just come here. Let me copy this one. I'll just give Control J. Yep. So I'll just give Python followed by the file name dot py. Yeah. The maximum distance, the diameter 4.24 we are getting, which is absolutely correct. We are getting the desired output, right? So we are done with the rotating calipers algorithm. So before moving on with the next algorithm, let me summarize whatever we have learned so far, right? So there are some 2 to 3 points which we have to remember at any cost, right? So just pay attention to this. So the first one here would be rotating calipers is an elegant big of n geometric method for analyzing convex polygons. For analyzing convex polygons, yeah, this we know. Next, let's move on with the second method. It is mainly used to find the diameter. Mostly we make use of it to this one, find the diameter actually. Just remember this one. Yeah, it is mainly used to find the this one diameter, minimum bounding box and width, minimum bounding box and width of polygons actually. Yeah, so this is fine. The third point here would be the algorithm rotates parallel lines around the convex shape. This we have discussed, testing extreme points efficiently without checking all the pairs, right? Which would take actually big O of n square, which would take actually big O of n square, right? So here this is the main this one. These are some of the main points that I wanted to discuss with you guys at any cost, right? So these are some of the points actually, right? So I hope these points are completely clear, man. You have to remember these points whenever we hear the rotating calipers algorithm. These 3 points that has to come this one in your mind actually. Yep, so this is fine. We are done with this algorithm. Now let's do one thing. Next let's discuss the, so what algorithms, what algorithm shall we discuss next actually? Let's go with a sweep line for the segment intersection, or you can just call this one as sweep line or line sweep for the segment intersection algorithm. Yep. So for now, this is it. Thanks for watching, guys.